In this third part of our three-part series on circular motion, we want to do an example that changes from a linear velocity to an angular velocity. And to do that, we can proceed as we have in the previous video, and let's write down the particular velocity that we know, or relationship that we know, and where is it that we want to end up. Linear velocity is a linear measurement per unit of time. We want an angular velocity, so it's got to be a rotational measure, either degrees or radians per unit of time. And we could proceed here as we did in part 2 and use the factor label approach, which means we're going to multiply 5 miles over 1 hour times a series of fractions to cancel out the miles and end up with degrees, and cancel out the hours and end up with seconds. And I imagine that we're all comfortable with the thought of changing from hours to seconds. So let's start there. And oftentimes, as you're working with problems that you're not exactly sure the path to go, pick out something that you do understand and begin there. It gives your brain some time to think while you're planning your next step. So we're going to change from hours to minutes by multiplying by 1 hour is 60 minutes, and we can see now that the hours will cancel. So then we want to cancel minutes and end up with seconds. Okay, no problem. We'll multiply by 1 minute over 60 seconds. So now if we were to multiply these three fractions together, canceling as we can, not just labels, but which in this case would be the minutes and the minutes and the hours and the hours. I'm sorry, I scrolled over the mile. But we can also cancel, the numbers as well, just to make the multiplication easier. I know we use those electronic brains and push buttons, but you want to make yourself think about things like just simply reducing a fraction or canceling without using the calculator. It builds your skill set to an automatic type of reaction that will put you in good position when you don't have that electronic brain with you. Okay, so back to what I was saying. If we do our multiplication and canceling, we're not going to end up with degrees on the top. We are going to end up with seconds on the bottom. So now we have the problem, how do we change from linear motion to rotational motion? And when we look up here at our relationships, thinking in terms of the basic unit of rotation that we talk about when we're looking at, say, a pulley or a fan as being revolutions per minute, second, whatever unit of time you're using, we can equate that one revolution to both an angular unit of measure, since one revolution would be one circle, therefore it's 360 degrees or 2 pi radians, and we can relate it to circumference, which in reality means when you measure around a circle, it's like cutting the circle and stretching it out as a line to measure it. It's a linear measurement. So we've got a linear measurement, 5 miles, that we need to turn into a rotational unit. And again, we can proceed in this multiplication. Okay, so we need to now concentrate on how to change the miles into degrees. Well, we know that if we multiply by this fraction, we have a little bit of comfort because all of a sudden we've interjected degrees in here. We still haven't canceled the miles, and now we have revolution. Yes, you have to love a revolution. Well, let's go there next. We know that one revolution is the same as one circumference, and now we're hopefully beginning to feel more at ease. And now we can get rid of the circumference by putting in what that circumference actually is. And in this case, remembering that the circumference is 2 times pi times the radius, which the radius is what we have, then our circumference here is 12 inches. And now notice that if we were to multiply everything together on top, we'd have degrees and miles instead of just degrees. And on the bottom, we'd have inches and seconds. So, inches and miles being both linear, I need to change one into the other in order to be able to cancel out that mile. So, let's work from large to small. That usually is more comfortable for us. So let's multiply by how many feet in a mile. And that'll cancel the mile. And then now all we need to do is multiply by something that will get rid of those feet. There we go. Now, let's go through and do the canceling. Okay, this 5, come on now, cancels with the 60, gives us 12. Hours cancels with hours. Minutes cancels with minutes. 60 will cancel with 360 and give us 6. And there's the degrees that we want to keep. We're going to cancel out the revolutions, the circumference. The 6 will cancel with the 12. Now we get rid of the miles. We can cancel this 12 with this 12. We can cancel the inches with the inches, the feet with the feet, the 2 with the 5,280, and we still have the pi in the denominator and 2,640 degrees. So at this point we have 2,640 degrees in pi seconds, but we don't want pi seconds. Our rates are always measured like miles per 1 hour, so it's always per 1 unit, in this case of time. So let's do the division and put our answer in tenths of a degree. So doing the calculation, we'll get 840.3 degrees in 1 second, which tend to read more in this way. DPSs, degrees per second. Now, let's go back and look at a formula that you've been using fairly frequently in the trig setting and science setting. This formula, which basically expresses the definition of a radian as long as that theta is in radians, and it's not valid if the angle isn't measured in radians. The definition of a radian, remember, says that a 1 radian angle, theta, tells you how many radii are contained in the arc that the angle cuts from the circle. So if we know the number of radians multiplied times the radius, whatever the unit of measure is for the radius will also be the unit of measure for the arc. Well, notice that S is a linear measurement, as is R, and theta here is an angle, and therefore it's a rotational thing. So not only do we use this in terms of the general expression of the definition of a radian that equates the radius to the length of an arc, it also can be looked at as saying, suppose I divide both sides here by time. And in this, on the right side, we want to actually split it apart so that R is the coefficient of the fraction theta over t. Now, what's the significance of that? On the left side, we have a linear distance, inches, feet, yards, meters, centimeters, in time. So we've got feet per second, miles per hour, whatever the units are. We have a linear velocity here. On the other side, here again, we want this to be in radians, or it's not valid. So radians per unit of time, well, that would be an angular velocity. So we have here a direct relationship from our arc length formula, or our definition of our radian, that directly relates linear velocity to angular velocity. Now, since this formula works for radians but not degrees, remember that if we want something in degrees, then we'd have to do a conversion. Also, in a problem of this particular nature, the example we've just worked, notice that even though this is a nice straightforward thing, it doesn't get you away from all of these conversions, really.